This is CPE 133. This is Introduction Experiment 3, and what we'll be doing here is using Verilog structural modeling to implement a 5-bit ripple carry adder. So this represents our introduction to structural modeling, which is what we'll be using the rest of the quarter. Super powerful, supports both hierarchical and modular design, which are the heart of digital design. And also this is an introduction to iterative modular design, and we'll talk more about that in a second. And so what we're going to do here is implement a ripple carry adder with our previously designed half and full adders, and then once we get that implemented, we're just going to test it visually on the development board. So this is a diagram of a 4-bit ripple carry adder, and the idea here is that this ripple carry adder is made up of a set of half and full adders. So the least significant bit over here is going to be a half adder. All the other bit locations are going to be full adders. So you need to use at least 2 levels in your design, which is essentially the structural modeling part of this. By all means, these signals are listed differently, but you need to use bus notation or bundle notation. And for this experiment, no need to simulate it. We'll come back and simulate this or something similar later. Now, the issue with this ripple carry adder is it adds a bit at a time. Well, it adds all the bits at the same time, but the bits may change. Bit locations may change based on this carry from a lower order bit to a higher order bit. So if there's a carry, it's going to change that higher order bit from what it was initially. So once again, these 4 elements are acting in parallel. They're actually calculating all the bit locations at the same time, but the bit location won't be right until the carry has rippled up from the lower bits. Our ripple carry adder, commonly known as RCA, is our first digital design foundation module, and this is our generic module here, where you got data coming in, data coming out, control coming in, and status coming out. And for our circuit here, we've got data coming in, we have no control signals. We got data coming out, and we have 1 status signal, which is the carry out. This is the black box diagram for experiment 3. It's a 5-bit ripple carry adder. Notice that the 2 operands A and B are 5 bits, as well as the sum. The carry out's a single bit. There is no carry in this because we are using a half adder in the lower bit position, which doesn't have a carry in. Quite frankly, probably should using a full adder so we can have a carry in, but more on that later. So the issue is that this is your first experiment with structural modeling, so the idea is to make it incredibly neat and organized, and one of the ways to do that is following the indentation rules. So this is true hierarchical modeling. It's what digital design is all about. I know Verilog structural modeling, initially it's kind of a pain in the butt, but after you do it a couple times, it gets makes more and more sense. And the issue is there is a structural modeling cheat sheet that I always use, because typically I forget how to do it, and then I end up cutting and pasting, and that's why I don't learn it, because once I do it, I cut and paste, and then my fingers don't do it. My brain doesn't do it, my fingers do it. And so once again, take a look at the cheat sheet. You're always welcome to use that anytime you do it. Make sure you use bundle notation wherever you can. You can do stuff like add bundles of A, plus B, etc., etc. If A and B are multiple bit values, it will add these directly and OR them, or whatever you want. So do not use single signals for this for anything other than the carry out. Internal signals you can use as a bus, or you can actually declare single signals if you want. It's probably better to use as a bus. So these here are the internal signals, which are these internal carries that the outside world does not know anything about.